For most of human history, space was not a destination. It was a mystery, an unreachable realm of lights fixed to the sky, governed by myth, philosophy, and imagination, rather than by engineering or experience. The stars marked time, guided travelers, and inspired stories, but they were never thought of as places that humanity might one day visit. Yet, over the course of centuries, that understanding began to change. Long before rockets thundered off launch pads or humans orbited the Earth, a quiet revolution was already underway. A revolution in how people understood the universe itself. When early astronomers turned telescopes toward the night sky, they did more than discover new celestial objects. They shattered the idea that Earth stood at the center of creation. They revealed that the heavens were not perfect or immutable, but physical places governed by the same laws that shaped the world beneath our feet. From those early observations grew a radical idea. If the universe was governed by universal laws, then space was not forbidden. It was simply unexplored. This video tells the story of how that idea became reality. It is the story of how centuries of scientific discovery, mathematical insight, and engineering ambition transformed space from an abstract concept into a domain of human activity. From Galileo's first observations and Newton's laws of motion, to the earliest rockets, Cold War competition, lunar landings, robotic explorers, space stations, and the rise of commercial spaceflight, this is a journey that spans more than 400 years of human thought and effort. Along the way, spaceflight became many things at once: a scientific endeavor, a political instrument, a technological proving ground, and ultimately, a shared human enterprise. It reshaped how we understand our planet, our solar system, and our place in the universe. Satellites changed daily life on Earth. Robots turned distant worlds into places we could study up close. Humans learned not just how to reach space, but how to live and work there for months, and eventually years at a time. And today, as new missions return samples from asteroids, probe the origins of the universe, test planetary defense, and prepare for a sustained return to the moon and beyond, the story of spaceflight is still unfolding. This is not just a history of machines and missions. It is a history of ideas, of persistence, curiosity, and the belief that exploration is possible even when the destination seems impossibly far away. This is the story of how humanity learned to leave Earth. The intellectual and technological foundations of spaceflight emerged gradually over several centuries, rooted not in rockets or spacecraft, but in the transformation of humanity's understanding of the cosmos during the scientific revolution. A decisive early moment occurred in 1610, when Galileo Galilei turned his improved telescope toward the night sky and published Sidereus Nuncius, reporting unprecedented observations that challenged long-held Aristotelian and Ptolemaic assumptions about the heavens. Galileo's discovery of 4 moons orbiting Jupiter demonstrated conclusively that not all celestial bodies revolved around Earth, undermining geocentrism and lending strong empirical support to the Copernican heliocentric model. His observations of mountains and craters on the moon further contradicted the notion that celestial objects were perfect and immutable, revealing instead that other worlds possessed physical landscapes analogous to Earth's. These revelations did more than reshape astronomy. They fundamentally altered humanity's conception of its place in the universe, encouraging the idea that the heavens were governed by the same physical laws as the terrestrial realm. This philosophical shift proved essential for the eventual emergence of astronautics, as it framed space not as a mystical or unreachable domain, but as a physical environment subject to investigation, measurement, and ultimately, travel. Building on this new observational tradition, Isaac Newton advanced the theoretical framework necessary to explain celestial motion and gravitational interaction. Newton's development of the laws of motion and universal gravitation in the late 17th century unified terrestrial and celestial mechanics, showing that the same forces governing a falling apple also determine the orbits of planets and moons. His construction of the first practical reflecting telescope in 668 further refined astronomical observation by reducing chromatic aberration, enabling clearer and more precise views of distant objects. Newton's mathematical formalization of motion laid the conceptual groundwork for understanding trajectories, velocities, and forces, concepts that would later become central to rocket science. Although Newton himself did not propose spaceflight, his famous thought experiment involving a cannon firing projectiles from a mountaintop implicitly illustrated the principle of orbital motion, foreshadowing the idea that a sufficiently fast projectile could continuously fall around Earth rather than returning to the ground. This insight, though abstract at the time, would later be recognized as a foundational description of artificial satellites. The 18th century witnessed further expansion of the known solar system, reinforcing the idea that space was vast, dynamic, and worthy of systematic exploration. In 1781, William Herschel's discovery of Uranus marked the first identification of a new planet in recorded history, made possible by telescopic observation rather than naked eye astronomy. Uranus's detection demonstrated that the boundaries of the solar system extended far beyond what classical astronomers had imagined, suggesting that humanity's celestial neighborhood was both larger and more complex than previously believed. Herschel's work also contributed to the study of nebulae and star clusters, stimulating debates about the structure of the Milky Way and the possibility of other island universes. This growing awareness of cosmic scale gradually shifted astronomy from a descriptive science focused on cataloging objects to an analytical discipline concerned with origins, structure, and physical processes. The discovery of Ceres by Giuseppe Piazzi in 1801 further transformed astronomical thought by revealing an entirely new class of objects within the solar system. Initially classified as a planet and later recognized as the largest asteroid, Ceres occupied the gap between Mars and Jupiter predicted by the Titius-Bode law. Its identification inaugurated the systematic study of minor planets and demonstrated that the solar system contained far more diversity than the traditional planetary model suggested. This realization had profound implications for later space exploration, as it highlighted the scientific value of small bodies as records of early solar system formation. The recognition that such objects could be tracked, predicted, and categorized reinforced confidence in the predictive power of celestial mechanics, an essential prerequisite for navigating spacecraft across interplanetary distances. As observational astronomy advanced, parallel developments in physics and engineering began to hint at the possibility of propulsion beyond conventional means. In 1813, William Moore articulated early principles resembling what would later be formalized as the rocket equation, describing the relationship between propulsion, mass, and velocity. Although Moore's work lacked experimental validation and remained largely theoretical, it represented an early attempt to quantify the requirements for self-contained propulsion systems capable of operating in a vacuum. These ideas challenged the prevailing assumption that motion required continuous contact with a medium, an assumption incompatible with space travel. By framing propulsion as a problem of momentum exchange rather than atmospheric interaction, Moore contributed to a conceptual shift that made rocket-based spaceflight scientifically plausible, even if technologically distant. Technological progress in optics and imaging during the 19th century further strengthened the empirical foundation necessary for contemplating spaceflight. In 1840, John William Draper produced the first successful photograph of the Moon, capturing surface details that surpassed what could be reliably recorded by hand. Lunar photography transformed the moon from a distant, abstract object into a tangible world with measurable features, fostering scientific interest in its geology and morphology. These early images enabled more accurate mapping of craters, maria, and highlands, laying groundwork for later considerations of landing sites and surface exploration. Photography also reinforced the notion that celestial bodies could be studied using the same empirical methods applied on Earth, further dissolving the conceptual boundary between terrestrial and extraterrestrial environments. Around the same time, advances in telescope design and observational technique led to deeper insights into the structure of the universe. In 1845, William Parsons, the third Earl of Rosse, used his massive Leviathan of Parsonstown telescope to observe spiral structures in objects then known as whirlpool nebulae, most famously M51. These observations hinted that some nebulae were not merely clouds of gas within the Milky Way, but potentially vast systems of stars in their own right. Although the true nature of galaxies would not be confirmed until the 20th century, Parsons' work expanded the perceived scale of the universe and suggested that space extended far beyond the immediate solar neighborhood. This growing cosmic perspective subtly influenced speculative thinking about humanity's long-term future, encouraging the idea that exploration might one day extend beyond Earth, the Moon, and even the planets. The latter half of the 19th century saw a convergence of scientific insight and imaginative speculation that brought the concept of space travel closer to serious consideration. In 1861, William Leach published one of the earliest systematic proposals for rocket-based spaceflight, arguing that rockets, rather than cannons or balloons, offered the most feasible means of reaching outer space. Leach recognized that propulsion in a vacuum was not only possible, but advantageous, anticipating key arguments later formalized by 20th century rocket pioneers. His work bridged the gap between theoretical physics and engineering imagination, presenting spaceflight not as fantasy, but as an engineering challenge, solvable through incremental advances. Perhaps the most influential figure in the theoretical development of astronautics during this period was Konstantin Tsiolkovsky, whose ideas synthesized centuries of scientific progress into a coherent vision of space exploration. In 1895, Tsiolkovsky speculated about a celestial castle, an early conceptualization of a space elevator, illustrating his willingness to think beyond conventional technological constraints. While this proposal remained speculative, it reflected a deep understanding of orbital mechanics and gravitational balance. Tsiolkovsky's most enduring contribution came in 1903, when he published his work on rocket motion, formally deriving the rocket equation and introducing the concept of multi-stage rockets. By mathematically demonstrating how a rocket's velocity depended on exhaust speed and mass ratios, Tsiolkovsky provided the essential analytical tool needed to design vehicles capable of reaching orbital and escape velocities. His recognition that staging could overcome the limitations of single-stage rockets transformed spaceflight from an abstract possibility into a theoretically achievable endeavor. Tsiolkovsky also articulated a broader philosophical vision in which space exploration was not merely a technical achievement, but a necessary step in humanity's evolutionary progress. He envisioned space stations, extraterrestrial colonies, and the eventual expansion of human civilization beyond Earth, framing spaceflight as both a scientific and cultural imperative. Although his work initially received limited attention outside Russia, it profoundly influenced later generations of engineers and thinkers, establishing a conceptual lineage that connected early astronomical observation to modern astronautics. Taken together, these developments illustrate that spaceflight did not emerge suddenly in the 20th century, but evolved through a long process of intellectual accumulation. From Galileo's telescopic revelations and Newton's laws of motion, to Herschel's planetary discoveries and Tsiolkovsky's mathematical formalism, each advance contributed a critical piece to the puzzle. Astronomy revealed the structure and scale of the universe. Physics explained the forces governing motion, and early engineering thought suggested mechanisms for propulsion beyond Earth. By the dawn of the 20th century, the theoretical groundwork for spaceflight was largely in place, awaiting only the technological innovations necessary to turn centuries of observation, calculation, and imagination into reality. While the 19th century established the theoretical plausibility of spaceflight, the early 20th century marked the crucial transition from abstract calculation and speculative vision to experimental engineering and practical rocketry. This transformation was driven by a small but determined group of pioneers who sought to convert mathematical principles into functioning machines capable of sustained, controlled propulsion beyond the limits of Earth's atmosphere. Central among these figures was Robert Hutchings Goddard, whose early work synthesized theoretical physics, experimental rigor, and engineering ingenuity into a coherent program for rocket development. In 1914, Goddard secured patents for multi-stage rockets and liquid fuel propulsion systems, recognizing that only such designs could overcome the limitations of solid propellants and single-stage configurations. His patents outlined concepts that would later become standard in modern launch vehicles, including fuel injection, combustion chambers, and staged mass reduction, demonstrating that rocketry was no longer merely an intellectual exercise, but an emerging technological discipline. Goddard's work was grounded not only in invention, but also in a systematic understanding of the physical challenges posed by high altitude and vacuum flight. In 1919, he published A Method of Reaching Extreme Altitudes, a landmark treatise that rigorously analyzed rocket performance in near-vacuum conditions and explicitly rejected the widespread misconception that rockets required atmospheric pressure to function. By demonstrating that thrust depended on momentum exchange rather than air resistance, Goddard addressed a fundamental barrier to acceptance of rocket propulsion. His analysis extended Tsiolkovsky's theoretical insights into a practical engineering context, bridging the gap between mathematical abstraction and experimental design. Although the publication was met with skepticism and, in some cases, ridicule, most famously from popular press outlets that misunderstood its claims, it nonetheless provided a scientifically sound framework that later engineers would adopt almost verbatim. Parallel to Goddard's efforts in the United States, Hermann Oberth emerged as a leading figure in Europe, further legitimizing rocketry as a scientific field. Oberth's 1923 book, Die Rakete zu den Planeten Roman, The Rocket into Planetary Space, articulated a comprehensive vision of spaceflight grounded in physics and engineering rather than fiction. He addressed propulsion efficiency, fuel chemistry, structural design, and the physiological effects of space travel on humans, presenting spaceflight as a multidisciplinary challenge requiring coordinated scientific solutions. Oberth's work was particularly influential because it circulated widely among students and amateur engineers, inspiring a generation of enthusiasts who would later become key contributors to national rocket programs. By treating spaceflight as a legitimate scientific pursuit, Oberth helped shift rocketry from the fringes of speculative thought into the mainstream of applied physics. These theoretical and conceptual advances soon found expression in organized experimentation. In 1924, the Soviet Union established the Society for the Study of Interplanetary Travel, reflecting a growing institutional interest in rocketry and space exploration. This organization brought together engineers, scientists, and visionaries who viewed spaceflight as both a technological challenge and a symbol of modern progress. Figures such as Sergei Korolev and Valentin Glushko, who would later play central roles in Soviet space achievements, were deeply influenced by this early culture of experimentation and collaboration. The society fostered a research environment in which theoretical discussion was closely linked to practical testing, reinforcing the idea that spaceflight was an achievable objective rather than a distant dream. The decisive experimental breakthrough came in 1926 when Goddard successfully launched the world's first liquid fuel rocket. Though modest in scale, the flight demonstrated the viability of liquid propulsion, validating years of theoretical analysis and experimental refinement. Liquid fuels offered higher efficiency, controllability, and scalability than solid propellants, making them essential for reaching orbital velocities. Goddard's launch marked the beginning of modern rocketry, establishing a technological lineage that would lead directly to later launch vehicles. Despite limited funding and persistent public misunderstanding, Goddard continued refining his designs throughout the 1930s, developing guidance systems, gyroscopic stabilization, and improved fuel delivery mechanisms. His work, often conducted in relative isolation, nonetheless laid the technical foundation upon which subsequent programs would build. In Europe, the Verein für Raumschifffahrt, VFR, or Society for Space Travel, formed in Germany in 1927 and quickly became a focal point for amateur and professional rocketeers alike. The VFR attracted individuals such as Wernher von Braun, who would later become one of the most influential figures in 20th century rocketry. The society conducted experiments with liquid fuel rockets, emphasizing hands-on testing and iterative design. These activities reflected a broader cultural enthusiasm for technological progress during the interwar period, when aviation, radio, and automotive engineering were rapidly advancing. Rocketry benefited from this environment, drawing on innovations in materials science, combustion chemistry, and mechanical engineering. Across Europe and the Soviet Union, rocket clubs proliferated throughout the 1930s, accelerating the pace of experimentation and knowledge exchange. These groups often operated with limited resources, relying on ingenuity and collaboration to overcome technical obstacles. They tested engine designs, propellant combinations, and stabilization methods, gradually improving performance and reliability. Although their stated goals often included peaceful exploration, the strategic implications of rocket technology did not go unnoticed. As liquid fuel rockets demonstrated increasing range and payload capacity, military institutions began to recognize their potential as weapons systems, particularly in an era marked by geopolitical tension and rapid technological competition. This shift toward military application culminated in the development of the German V-2 rocket during the Second World War. Designed under the leadership of von Braun and his team, the V-2 represented the first large-scale, operational, liquid-fuel ballistic missile. In 1942, it became the first human-made object to reach the edge of space, crossing the Kármán line during test flights. Technologically, the V-2 embodied many of the principles articulated by earlier pioneers: liquid propulsion, gyroscopic guidance, and staged combustion processes. Its successful operation demonstrated that rockets could achieve velocities and altitudes previously considered unattainable, conclusively proving the feasibility of spaceflight from an engineering standpoint. The V-2's development also revealed the profound dual-use nature of rocket technology. While its primary purpose was military, the data and experience gained from its design and operation proved invaluable for post-war space programs. The rocket's ability to traverse the upper atmosphere provided unprecedented opportunities for scientific measurement, including studies of atmospheric composition, radiation, and microgravity effects. In this sense, the V-2 served as an unintended bridge between wartime weaponry and peaceful space exploration, illustrating how technological advances driven by conflict could later be repurposed for scientific discovery. Following the end of the Second World War, captured V-2 hardware and personnel became central to the emerging rocket programs of both the United States and the Soviet Union. In the United States, Operation Paperclip facilitated the transfer of German engineers, including von Braun, who would later contribute to the development of American launch vehicles. Similarly, the Soviet Union integrated captured technology and expertise into its own missile and rocket initiatives, accelerating its progress toward orbital capability. These efforts marked the institutionalization of rocketry, as governments began investing heavily in research facilities, testing infrastructure, and long-term development programs. The post-war period thus represented a turning point in the history of spaceflight, as rocketry transitioned from a marginal pursuit to a strategic priority supported by state resources. The convergence of theoretical insight, experimental validation, and industrial capacity created conditions under which sustained progress became possible. Rocket design evolved rapidly, incorporating advances in materials, science, electronics, and control systems. Engineers refined propulsion efficiency, improved guidance accuracy, and increased payload capacity, gradually approaching the thresholds required for orbital flight. Equally important was the cultural and intellectual shift that accompanied these developments. Spaceflight was no longer viewed solely as a speculative or futuristic concept, but as a practical extension of existing technological trends. The experiences of early pioneers demonstrated that complex, interdisciplinary challenges could be addressed through systematic experimentation and collaboration. This mindset would prove essential as space programs expanded in scale and ambition during the Cold War, requiring coordination among thousands of scientists, engineers, and technicians. In retrospect, the emergence of modern rocketry during the early 20th century can be understood as the culmination of centuries of scientific inquiry and decades of experimental persistence. Goddard's patents and publications provided the technical blueprint. Oberth's writings inspired a generation of practitioners, and organized societies created communities of practice that sustained innovation. The V-2, despite its destructive purpose, validated the core principles of rocket propulsion and demonstrated the feasibility of reaching space. The subsequent transfer of knowledge and technology ensured that these lessons were not lost, but instead formed the foundation for the space age that would soon follow. By the mid-20th century, the essential components of spaceflight liquid fuel propulsion, guidance and control, and staged mass reduction were firmly established. What remained was the application of these technologies toward peaceful exploration and scientific discovery. The groundwork laid by early rocketeers thus made possible the dramatic achievements of the post-stage Sputnik era, linking the experimental launches of the 1920s and 1930s directly to humanity's first steps beyond Earth. The onset of the space age in the late 1950s was not simply a sudden leap into orbit, but the culmination of decades of ballistic missile development, wartime rocketry, and a rapidly intensifying Cold War competition in science and technology. In 1957, the Soviet Union's launch of Sputnik 1 became the decisive watershed because it achieved two things simultaneously. It proved that a human-made object could be placed into sustained orbit around Earth, and it did so under conditions of geopolitical rivalry that instantly magnified the accomplishment into a global event. Sputnik's steady radio beeps were technologically simple, yet symbolically profound, because they signaled not only a new era of scientific capability, but also the emergence of long-range rocketry as a strategic reality. The public perception of Sputnik as a surprise owed much to the fact that many observers, especially outside specialized scientific circles, had not fully grasped how wartime rocket work and post-war missile programs had matured. In reality, Sputnik was embedded in a wider international context, that included the International Geophysical Year, IGY, an ambitious scientific initiative that encouraged geophysical and atmospheric research and gave additional legitimacy to satellite launches as instruments for observation. The Soviet achievement nevertheless had immediate psychological and political impact, prompting urgent questions in the United States about education, research investment, and national security, and accelerating institutional decisions that would shape the next decades of exploration. The Soviet program quickly followed Sputnik with additional feats designed to demonstrate that orbit was not a singular stunt, but a repeatable capability. Laika's orbital flight, soon thereafter, represented an ethically complex but technically significant step. It tested life support constraints and biological responses in space, making the question of human survivability more concrete. Even though the mission's humanness has been widely criticized in historical reflection, it underscored the grim reality that early space exploration took place in an environment where engineering uncertainty was high and political incentives favored rapid demonstration over cautious incrementalism. From a technical standpoint, these early flights forced engineers to confront problems that would remain central for decades: thermal regulation, atmospheric control, mass constraints, communications reliability, orbital tracking, and the challenges of re-entry and recovery. Each of these requirements pushed beyond the older logic of missiles, where reaching a target mattered more than sustaining an environment for living organisms or returning hardware intact. In the United States, Sputnik catalyzed rapid organizational change and a surge of public investment. The founding of NASA in 1958 represented the most visible institutional response, transforming the earlier aeronautics-oriented framework into a national civilian space agency capable of coordinating large projects across government, industry, and academia. NASA's early direction reflected a dual ambition: to establish U.S. credibility in orbit quickly and to develop longer-term capabilities for human spaceflight and scientific observation. The discovery of the Van Allen radiation belts by Explorer 1, launched in 1958, helped validate the scientific promise of satellites by showing that spaceborne instruments could reveal previously unknown features of Earth's near-space environment. Just as importantly, that discovery reshaped engineering assumptions about radiation exposure and spacecraft design, making clear that the region beyond the atmosphere was not an empty void, but an environment with hazards that demanded shielding, careful trajectory planning, and robust electronics. In this way, early satellite science was not merely an academic exercise. It directly informed the design requirements for later crewed missions and deep space probes, linking scientific discovery to operational necessity. The leap from satellites to human spaceflight required an additional conceptual shift. It demanded that engineers design systems not just to place objects in orbit, but to sustain life, ensure safe re-entry, and manage risk in a domain where failures were often catastrophic. The Soviet Union's success in placing Yuri Gagarin into orbit in 1961 therefore became a second defining moment of the space age. Gagarin's flight demonstrated that human beings could endure launch forces, microgravity, and re-entry conditions, and it provided an enormous propaganda victory by associating Soviet political identity with scientific modernity. Yet, even here, the accomplishment was inseparable from engineering realities. The mission required reliable guidance, stable orbital insertion, controlled re-entry, and a recovery process that could retrieve both the cosmonaut and mission data. In the United States, Alan Shepard's suborbital flight shortly afterward marked an early but crucial milestone, affirming that the U.S. could send a human into space and recover him safely even as it continued to pursue orbital capability. These first crewed missions were necessarily conservative in scope because they occurred when the margin for error was narrow, spacecraft were compact, mission durations were short, and operational procedures prioritized basic survival over complex tasks. The early focus on proving, "Can we do it?" was a prerequisite for later questions. How long can we do it? What can we do while there? And how can we do it repeatedly? As the 1960s progressed, human spaceflight rapidly diversified beyond the initial demonstration flights. Valentina Tereshkova's mission in 1963, which made her the first woman in space, highlighted both the Soviet Union's willingness to expand the symbolic dimensions of exploration and the fact that crew selection and representation were inherently political as well as technical. Her flight challenged assumptions, common at the time in many societies, about who could serve as a space traveler, and it showed that the physiological demands of spaceflight were not exclusive to a narrow demographic. From a programmatic standpoint, such missions also served a strategic purpose. They sustained a narrative of steady progress and innovation, keeping the Soviet program visibly in the lead at a time when the United States was mobilizing significant resources to catch up. A similarly dramatic evolution occurred with extravehicular activity, EVA, which posed a different class of challenge than simple orbital survival. Alexei Leonov's first spacewalk in 1965 proved that a human could exit a spacecraft and function in open space, but it also revealed how unforgiving that environment could be. EVA demanded pressure suits that could balance flexibility with life support, thermal management, and micrometeoroid protection. It required tethers, handholds, and procedures that anticipated disorientation, limited mobility, and the absence of familiar sensory cues. Even apparently minor difficulties, like a suit expanding or stiffening, could quickly become life-threatening. Leonov's experience therefore functioned both as a triumph and as a warning, leaving the protective shell of a spacecraft multiplied risk, and successful EVA would require careful engineering iteration, extensive training, and an operational culture that treated procedure as a form of life support. In the United States, these realizations shaped the trajectory from Mercury to Gemini, a progression that illustrates how early programs often serve as stepping stones rather than endpoints. Mercury's essential purpose was to prove the feasibility of human spaceflight and recovery. Gemini's purpose was to cultivate the operational techniques necessary for more ambitious missions, especially lunar expeditions. The Gemini program therefore emphasized three critical competencies: extended duration, rendezvous and docking, and EVA. Extended duration mattered because reaching the moon and returning would require astronauts to remain functional for days rather than hours, and future deep space ambitions would demand even longer endurance. Rendezvous and docking mattered because lunar mission architectures, especially those involving separate landers and command modules, required spacecraft to meet and connect reliably in orbit. EVA mattered because lunar exploration and spacecraft assembly tasks demanded that humans function effectively outside vehicles, whether in Earth orbit or on the lunar surface. Gemini treated these competencies as engineering and operational problems to be solved through repeated flights, each designed to test specific capabilities and refine procedures. Rendezvous, for instance, was not simply a matter of flying toward another spacecraft. It required a deep understanding of orbital mechanics, where objects in different orbits do not behave like aircraft in the atmosphere. Matching velocity, phasing trajectories, and executing burns with precision were essential, and these tasks demanded both computational assistance and human judgment. Docking similarly required mechanical interfaces that could tolerate slight misalignments, control systems capable of fine maneuvering, and astronaut training that prepared crews for a task that was cognitively demanding under time pressure. The incremental successes of Gemini thus built confidence not by a single dramatic event, but by establishing repeatability. A procedure that can be done once is a demonstration, but a procedure that can be done reliably becomes infrastructure. EVA development followed a comparable learning curve. Early American spacewalks encountered difficulties that echoed the Soviet experience: limited mobility, fatigue, and the realization that movement in microgravity requires stable anchoring and careful body positioning. The solution was not simply more bravery, but a redesign of tools, handholds, and suit systems, plus an evolving understanding of how humans work in weightlessness. Gemini missions forced NASA to confront the fact that operational success in space depends on the integration of human physiology and mechanical design. The astronaut is not just a passenger, but a component in a complex system. And the system fails if either the machine or the human-machine interface is inadequate. By the mid-1960s, therefore, the space age had progressed beyond the initial spectacle of firsts and into a phase where the central challenge was operational mastery. Sputnik and the first human flights established that orbit was possible and that humans could survive there. Explorer 1 demonstrated that satellites could transform scientific understanding, and Gemini showed that complex maneuvers could be performed repeatedly and safely enough to support bolder goals. In this sense, the early space age should be understood not as a linear race of headlines, but as an accelerating process of capability accumulation. Each milestone generated new questions and revealed new constraints, and the process of answering those questions through engineering, training, and institutional learning created the platform upon which lunar missions could soon be built. The transition from Earth orbital operations to lunar exploration represented an escalation not merely in distance, but in the complexity of systems, engineering, mission planning, and political commitment. Once rendezvous, docking, extended duration, and EVA had been demonstrated as practical capabilities, the Moon became the next logical proving ground for deep space crewed operations, a domain where communication delays, harsher radiation conditions, navigation constraints, and the irreversibility of many failures demanded a more rigorous approach than early orbital flights. Apollo 8's 1968 mission, which carried the first humans to orbit the Moon, served as a pivotal demonstration that the fundamental architecture of lunar flight, translunar injection, deep space navigation, lunar orbital insertion, and return re-entry could be executed reliably enough to justify an attempt at landing. The achievement was not simply technical, it was also psychological. Orbiting the Moon reframed it from a distant symbol into a reachable destination, and it signaled that deep space crewed flight had moved from conjecture to operational fact. Apollo's approach to the Moon was built on the recognition that achieving a landing required a tightly integrated system rather than a single remarkable rocket. The Saturn V's lift capability, the command and service module's life support and propulsion, the lunar module's specialized landing design, and the mission control infrastructure on Earth formed a single coordinated enterprise. This enterprise demanded a new scale of reliability engineering, redundancies, test programs, quality control procedures, and formalized decision structures became essential because failure modes multiplied as mission duration and distance increased. Lunar missions also required a new sophistication in navigation and computing. In deep space, a small error in velocity or timing can produce vast divergence in trajectory, and correcting it may consume limited propellant reserves. As a result, Apollo's success depended on precise calculations, reliable onboard instrumentation, and ground-based tracking that could reconstruct spacecraft position and velocity and then translate those into actionable guidance decisions. The Moon, in short, required a fusion of astrophysics, mechanical engineering, materials science, human factors design, and organizational coordination at a level that surpassed earlier programs. Apollo 11's 1969 landing, when Armstrong and Aldrin walked on the lunar surface, became the defining image of 20th century space exploration because it combined technical mastery with a narrative of human presence on another world. Yet the landing's significance is best understood as the culmination of a chain of preparations rather than an isolated triumph. Landing a crewed vehicle required not only reaching the lunar vicinity, but also understanding the surface environment well enough to choose safe regions and to design landing systems that could tolerate unknowns. The lunar surface presented uncertainties about dust behavior, bearing strength, terrain hazards, and lighting conditions. A successful landing therefore depended on preliminary reconnaissance, mapping, and surface assessment missions, many of which were robotic. These robotic missions were not secondary. They were enabling steps that translated the moon from a target into a place with physical properties that could be planned around. In that enabling role, the Soviet Luna program and the U.S. Ranger and Surveyor series were foundational. The Soviet Union achieved the first soft lunar landing in 1966, demonstrating that controlled descent to another body was possible and inaugurating a new era of robotic planetary engineering. Soft landing demanded precise descent engines, altitude sensing, and automated control systems that could respond faster than human operators due to communication delays. The U.S. Ranger missions, meanwhile, were designed to return close-range imagery during impacts, providing increasingly detailed views of lunar terrain that improved hazard assessment and site selection. Surveyor missions went further by performing soft landings and transmitting surface photographs and other data, offering evidence about soil mechanics and surface composition. Together, these robotic efforts provided a scaffold of knowledge. They reduced uncertainty about what spacecraft would encounter and allowed engineers to design landers with a clearer understanding of the real lunar environment. The interplay between robotic precursor missions and crewed landings illustrates an enduring pattern in space exploration. Robots often serve as the vanguard that converts uncertainty into data, thereby making human missions more feasible and less risky. After Apollo 11, the subsequent 6 Apollo missions over the next 3 years demonstrated that deep space crewed operations could be sustained repeatedly, expanding not only the number of landings, but also the scope of activities performed on the surface. Repeatability matters in technological history because it marks the shift from a singular feat to a matured capability. Each mission carried lessons forward, refining landing techniques, improving surface operations, and extending mission duration. Over time, lunar excursions became more scientifically ambitious, incorporating more extensive sampling, longer traverses, and more complex surface experiments. By repeatedly placing crews on the moon and returning them safely, Apollo established a practical precedent for crewed exploration that later programs would study, even when budgets and political conditions no longer supported lunar landings. At the same time, lunar exploration unfolded within a broader expansion of interplanetary ambition. The same rocketry and guidance advances that made the moon reachable also made planetary flybys possible. Mariner probes achieved flybys of Venus and Mars, demonstrating that spacecraft could navigate across interplanetary distances and return data from entirely different worlds. Planetary flybys were transformative because they replaced telescopic inference with direct measurement. Where Earth-based observations were limited by atmospheric distortion and distance, close flybys could measure atmospheric composition, magnetic fields, radiation environments, and surface properties. In doing so, they helped create planetary science as a modern empirical discipline. These early probes also revealed a deeper truth about exploration. Reaching another planet is not the end of the problem. It is the beginning of learning how unfamiliar that world actually is. Early Mars data, for example, forced rethinking of assumptions about habitability and surface conditions, while Venus measurements confronted scientists with the reality of extreme atmospheric pressures and temperatures. Each probe thus served a dual function. It expanded knowledge and corrected misconceptions. Simultaneously, the early space age generated practical applications that reshaped life on Earth and broadened political support for space programs beyond prestige. TIROS weather satellites transformed meteorology by enabling regular, global cloud imaging and atmospheric observation. The importance of this shift cannot be overstated. Weather forecasting improved not merely incrementally, but structurally, because satellites introduced a global observational perspective impossible from surface stations alone. This capability affected agriculture, disaster preparedness, shipping, aviation, and military planning, and it demonstrated that space systems could produce immediate public benefits. In a similar vein, early communication satellites enabled new forms of global connectivity, including the expansion of television and long-distance telephony. These satellites required different design priorities than crewed spacecraft or planetary probes. Stable orbits, long operational lifetimes, reliable power generation, and robust transponders became central. Yet they relied on the same underlying infrastructures: launch vehicles, tracking networks, and orbital mechanics expertise, meaning that scientific and commercial progress reinforced each other. The space age thus quickly became more than exploration. It became a new layer of technological civilization built around orbital assets. The cumulative effect of these developments was to widen the meaning of spaceflight. In the public imagination, Apollo defined the era. But in technical reality, the space age was a complex tapestry of mission types: crewed flights proving deep space operations, robotic probes extending science to other planets, and satellites transforming Earth observation and communication. These strands were mutually reinforcing. Improvements in guidance and propulsion developed for lunar missions benefited planetary probes. Tracking and telemetry infrastructure built for scientific missions supported communication satellites, and public enthusiasm for Apollo helped justify investments whose benefits spilled into weather forecasting, broadcasting, and global infrastructure. This cross-fertilization illustrates why space exploration cannot be reduced to a single narrative of flags and footprints. It is a systemic transformation of engineering capacity, scientific knowledge, and societal infrastructure. Seen as a whole, the period from the late 1960s into the early 1970s marked the maturation of spaceflight into an integrated enterprise. Apollo demonstrated that humans could operate around and upon another world. Robotic programs showed that precision landing and planetary encounter were possible without crews, and early satellite applications proved that space technology could deliver tangible, everyday value on Earth. Together, these achievements established that the question was no longer whether space could be reached, but what purposes: scientific, political, commercial, and ultimately civilizational spaceflight would serve. As the initial crescendo of lunar landings receded, the strategic and scientific center of gravity in human spaceflight shifted toward a different challenge: not traveling farther for brief visits, but staying longer and learning how to live and work in space as a sustained condition. This emphasis on long-duration habitation reflected both pragmatic constraints and evolving priorities. Deep space exploration demanded knowledge of how the human body and mind respond to weeks and months in microgravity, and it required the development of operational routines for maintenance, repair, resupply, and scientific work in a confined environment. Space stations therefore emerged as laboratories not only for science, but for human adaptation and systems engineering. The first space station, Salyut 1 in 1971, signaled the Soviet Union's determination to pursue a path that prioritized duration and incremental capability building. Unlike short crewed missions, a station creates an ongoing platform. It can host multiple crews over time, support a range of experiments, and evolve through learning and refurbishment. Yet building such a platform also intensifies complexity, because it requires life support systems capable of extended operation, power systems that can endure orbital cycling, and procedures for safe docking and habitation that can be repeated reliably. Salyut 1 inaugurated the practical reality that a space station is not merely a larger spacecraft. It is an ecosystem of interdependent subsystems. Environmental control and life support must manage air composition, humidity, temperature, and waste. Power systems must provide stable electricity for instruments and habitation. And attitude control must maintain orientation for thermal stability, communications, and docking operations. Furthermore, the station's purpose, long-duration work, means that the crew must be able to conduct maintenance and respond to anomalies. This requirement changes the relationship between humans and machines. Crews are no longer short-term occupants executing a pre-planned script, but active managers of a habitat that must remain functional across many weeks. The engineering of a station therefore becomes inseparable from the engineering of human procedures, training, and operational culture. In the United States, Skylab's launch in 1973 represented a parallel commitment to the long-duration model, though shaped by different institutional and political conditions. Skylab demonstrated that the U.S. could create a large orbital workshop capable of supporting extensive scientific research and extended habitation. The station's scientific agenda reflected the breadth of what a stable platform could enable: Earth observation, solar observation, microgravity experiments, and biomedical studies all benefited from having a crew and instruments in orbit for substantial periods. Skylab also illustrated a key virtue of stations: they provide continuity. Rather than designing a new spacecraft for each discrete goal, a station offers a reusable environment where different investigations can be conducted and refined over time. In this way, space stations function like orbiting laboratories, analogous to research vessels at sea or Antarctic bases on Earth, remote platforms that justify their cost by hosting diverse and evolving scientific programs. The mid-1970s also brought a symbolic shift toward cooperation with the Apollo-Soyuz mission in 1975, which joined American and Soviet spacecraft in a joint operation. The mission had practical significance in demonstrating docking compatibility and coordinated procedures, but its deeper meaning lay in showing that spaceflight could be a venue for diplomacy rather than purely competition. This cooperative moment did not erase geopolitical rivalry, but it established that technical interoperability and joint missions were possible, a precedent that would later become essential for multinational station projects. The requirement for joint operations pushes programs towards standardization, docking systems, communications protocols, and safety procedures must be coordinated, and this coordination itself becomes a form of infrastructure. Apollo-Soyuz thus foreshadowed a future where the scale and cost of space projects would encourage shared responsibility. The Soviet Union's Mir station, launched in 1986, became the most prominent embodiment of long-duration habitation in the late Cold War era. Mir advanced the station concept by serving as a modular platform that could be expanded and reconfigured. Modularity matters because it allows capabilities to grow through incremental launches, rather than requiring a single monolithic structure from the outset. It also enables redundancy and specialization. Different modules can host particular laboratories, living quarters, or docking ports, and failures in one area may be isolated rather than catastrophic for the entire station. Mir's long operational life also contributed uniquely to biomedical and operational knowledge. Extended missions revealed how microgravity affects muscle mass, bone density, cardiovascular function, immune response, and sensory orientation. These findings were crucial because they moved human factors from speculation to data. If humans were ever to travel beyond low Earth orbit for months at a time, The medical realities of microgravity would have to be addressed through exercise regimens, nutritional strategies, and eventually technological countermeasures. Mir also demonstrated the social and psychological dimensions of living in space. A station is an extreme environment where isolation, confinement, and dependence on complex systems can amplify stress. Long-duration crews must maintain routines, manage interpersonal dynamics, and sustain cognitive performance under conditions that offer little privacy and a constant awareness of risk. Operationally, Mir required ongoing resupply, repairs, and improvisation, underscoring that space habitats will inevitably encounter anomalies that cannot always be predicted on the ground. The station therefore became a proving ground for resilience. Crews and ground teams had to develop a culture of problem-solving that balanced procedure with adaptability. These lessons later influenced how space agencies thought about mission design and crew support, reinforcing the idea that success in space is as much organizational as technological. The Shuttle Mir program later served as a bridge between American and Russian experience, combining U.S. shuttle logistics and operational practices with Russian long-duration station expertise. This collaboration had practical benefits in preparing for a larger, more complex multinational station. It also demonstrated an important institutional truth. Spaceflight capabilities are distributed. Different programs develop strengths under different constraints, and collaboration can combine these strengths in ways that neither program could achieve alone. The transition from Cold War competition to post-Cold War cooperation thus had a technical dimension. Shared missions created shared standards, shared training practices, and shared expectations about safety and operations. The International Space Station, IS, whose construction began in 1998 and which has been continuously inhabited since 2000, represents the most enduring and complex realization of the station model. Its significance lies in its role as both an engineering object and a political structure. The IS required multiple nations to coordinate hardware development, launch schedules, funding commitments, and operational responsibilities over decades. This coordination demanded long-term governance mechanisms, agreements about resource allocation, crew time, research priorities, and safety standards. In technical terms, the IS required assembly in orbit, a process that relied heavily on docking, robotics, EVA, and careful choreography of modules and visiting vehicles. The station's continued habitation created a continuous human presence in orbit, turning spaceflight from episodic missions into a sustained human activity. Continuous presence matters because it transforms the nature of research. Long baselines allow longitudinal biomedical studies, repeated experimental replication, and continuous monitoring of Earth and the space environment. The IS also demonstrated the evolving role of stations as hubs in a broader space ecosystem. A permanently inhabited station requires logistics, food, water, spare parts, scientific payloads, and crew rotations. This need stimulates the development of cargo vehicles and operational routines that resemble supply chains more than heroic expeditions. Over time, this logistical perspective encourages thinking about space as a domain of operations rather than merely exploration. In other words, once humans live somewhere continuously, the central question becomes how to maintain the infrastructure that makes that life possible. The IS therefore functions as a testbed, not only for science, but for the practice of space operations at scale. China's entry into the station era with the Tiangong program in 2011, and the completion of a modular station in the early 2020s, further illustrates the normalization of long-duration habitation as a marker of mature space capability. A modular station requires mastery of rendezvous and docking, life support, power generation, crew training, and mission planning across repeated cycles. It also reflects a strategic decision to invest in continuity and national capacity. As more nations develop orbital stations or station-like platforms, the idea of humans routinely living and working in orbit becomes less exceptional and more institutionalized. Multinational crews living for extended periods underscore a broader trend. Spaceflight has increasingly become a shared endeavor, shaped by cooperative frameworks as well as competition. Across these station milestones, Salyut 1, Skylab, Apollo-Soyuz, Mir, the IS, and Tiangong, the underlying historical arc is the gradual transformation of orbit into a place of sustained human activity. Stations shifted human spaceflight away from brief demonstrations and toward the long-term project of adaptation, adapting bodies to microgravity, adapting engineering to continuous operation, adapting organizations to multinational governance, and adapting culture to the reality that space can be a workplace. This shift did not replace the dream of deep space exploration. Rather, it supplied the necessary foundation for it. Long-duration stations generate the biomedical data, operational habits, and technical reliability that future missions beyond low Earth orbit will require. In that sense, the station era should be understood as the patient construction of capability, less dramatic than lunar landings, perhaps, but indispensable to any future in which humans travel farther and remain longer beyond Earth. If the Apollo era demonstrated that humans could travel beyond Earth orbit and operate on another world, the Space Shuttle era reframed the central ambition of human spaceflight around a different premise: that access to orbit could become routine, flexible, and operationally reusable, rather than episodic and disposable. The first shuttle mission, flown by Columbia in 1981, inaugurated this new approach by introducing a spacecraft system designed for repeated use, with an orbiter that could launch vertically as part of a rocket stack and return to land on a runway, blending elements of rocketry and aviation into a single integrated architecture. The significance of this design was not merely technical. It represented an institutional and cultural attempt to turn spaceflight into a sustainable operational capability. A reusable spacecraft promised, at least in principle, to reduce costs through refurbishment, increase flight cadence through repeated use, and enable new classes of missions requiring crew presence, large payload bays, and the ability to retrieve or service hardware in orbit. The shuttle's existence therefore reoriented human spaceflight away from singular destination-driven achievements and toward the creation of an orbital transportation and work platform, an approach more consistent with a long-term presence in space. This shift in emphasis affected not only the kinds of missions undertaken, but also the kinds of engineering and management problems that mattered most. A reusable system must be safe and reliable across many flights, which means design decisions cannot be evaluated solely by whether they work once, but by whether they work repeatedly, predictably, and within a complex maintenance ecosystem. Reusability also changes risk accounting. Whereas a one-off spacecraft may accept certain margins for a single mission, a reusable vehicle carries accumulated wear, refurbishment variability, and operational pressures to maintain schedules. In the shuttle program, this tension between ambitious operational goals and the realities of complex hardware became a defining feature. The shuttle's early success demonstrated that reusable spacecraft operations were possible, but it also revealed that reusability does not automatically equate to simplicity. Instead, it can introduce new layers of inspection, refurbishment, and procedural burden that become central to the system's safety case. The Challenger tragedy in 1986 reshaped NASA's safety culture and stands as a stark reminder that mature operations are not immune to catastrophic failure. While the details of the accident belong to a broader analysis of organizational decision-making, engineering constraints, and environmental conditions, The historical significance within the arc of spaceflight lies in how the event changed assumptions about routine access to space. The shuttle had been conceived in part as a system that could fly frequently, carrying diverse payloads and crews, yet Challenger demonstrated that the coupling of complex technology with schedule pressure and institutional momentum could produce outcomes incompatible with the vision of routine operation. In the program's aftermath, safety culture became not merely a slogan, but a formal domain of organizational practice. Processes for anomaly reporting, launch readiness decision-making, risk communication, and engineering authority were reconsidered in an effort to reduce the probability that warning signs could be normalized or minimized. Despite these risks, the shuttle era generated a set of capabilities that proved crucial for both space science and the construction of orbital infrastructure. One of the shuttle's most celebrated accomplishments was its deployment and servicing of the Hubble Space Telescope, a mission profile that exemplified the shuttle's unique value. A crewed vehicle with a large payload bay, robotic arm capacity, and EVA capability could place major scientific instruments into orbit and later return to repair or upgrade them. This servicing capacity is historically significant because it altered the life cycle assumptions of space-based observatories. Prior to such missions, a telescope launched into orbit was often treated as deploy and hope, with limited possibilities for correction after deployment. Servicing changed that equation. It created a model in which complex orbital platforms could be maintained and improved, extending scientific lifetimes and enabling iterative upgrades that kept instruments near the frontier of capability. More broadly, Hubble servicing served as a proof of concept for on-orbit maintenance as a general operational paradigm, an idea that would later influence both government and commercial thinking about how to manage expensive orbital assets. The shuttle's role in building the International Space Station, ISS, throughout the 1990s and 2000s further reinforced the notion that human spaceflight could be oriented toward infrastructure rather than solely exploration. Constructing a space station is fundamentally a logistics and systems integration problem. Large components must be launched, assembled in orbit, connected through mechanical and electrical interfaces, and tested as they become part of a single functioning habitat. While some assembly could be automated, the complexity of alignment, verification, and contingency response made crewed participation valuable, and the shuttle became one of the workhorses of that assembly process. In this context, the shuttle's payload bay and robotic manipulation capacity were not just conveniences. They were enabling features that allowed large modules and trusses to be delivered and positioned with precision. EVA, in turn, became a construction methodology. Astronauts in suits performed tasks analogous to orbital shipbuilding, connecting cables, installing components, and conducting inspections. Over time, this pattern of work demonstrated that space construction is possible. But it also made clear that such construction depends on robust planning, standardized interfaces, disciplined procedures, and a willingness to treat orbit as an active worksite. The shuttle's retirement in 2011, after 35 missions, marked the end of an era and forced a reassessment of what reusability should mean in practice. In one sense, the shuttle demonstrated that reusable orbiters could indeed fly many times and accomplish extraordinary tasks, from satellite deployment to telescope servicing to station assembly. In another sense, the program revealed the limitations and costs associated with refurbishing a complex crewed spacecraft after each flight. The retirement, therefore, did not represent a rejection of reusability as an idea, but rather an opening for reusability to be reinterpreted and redesigned. The period after retirement was shaped by a shift in how reusability might be implemented, instead of a winged orbiter requiring extensive post-flight inspection and refurbishment. Emerging systems explored reusability at the level of boosters and stages, aiming to recover the most expensive hardware components in a way that could be repeated with less labor-intensive turnaround. This reorientation toward new reusability concepts was mirrored by the rise of private spaceflight efforts that sought to demonstrate that non-government entities could achieve crewed spaceflight milestones. Spaceship One's achievement of the first private crewed spaceflight in 2004 became a symbol of this broader shift, showing that innovation and risk-taking could occur outside traditional national programs, and that spaceflight could become part of a commercial ecosystem. Although Spaceship One was not an orbital vehicle, its historical importance lay in the proof of principle that private funding, private engineering teams, and alternative program structures could accomplish high-profile achievements. This, in turn, influenced how governments and agencies thought about procurement and partnerships, helping open pathways for commercial services and hybrid models in which public goals could be pursued through private vehicles and operations. The emergence of reusable boosters as a defining feature of commercial launch systems further illustrates how the post-shuttle era transformed reusability from a single program's architecture into a broader design philosophy. Reusable boosters changed the economics and cadence logic of launch by treating the first stage not as expendable hardware, but as an asset capable of multiple flights, in principle reducing per-launch marginal cost and enabling more frequent access to orbit. Historically, this matters because launch cost and launch frequency shape what kinds of missions are feasible. When launches are rare and expensive, missions tend to be highly consolidated, conservative, and risk-averse. When access becomes more frequent, experimentation becomes more plausible, constellations become economically rational, and the diversity of payloads expands. Thus, the post-shuttle commercial reusability movement is not simply an engineering story, but a structural shift in the space ecosystem, changing the underlying constraints that govern scientific, commercial, and governmental planning. Taken together, the shuttle era and its aftermath can be understood as a transition from heroic exploration toward operational spaceflight. Though neither mode fully replaces the other, the shuttle demonstrated the power of a reusable crewed platform to conduct complex orbital work, deploying and servicing Hubble, constructing the ISS, and enabling a wide range of mission types, while also revealing the persistent difficulty of balancing ambitious operational goals with the uncompromising demands of safety and reliability. Its retirement did not end reusability. Rather, it redistributed the concept, inspiring new architectures that emphasized recovered boosters and commercially driven launch systems. In this sense, the shuttle's legacy is not only what it accomplished, but how it expanded the menu of possibilities for what spaceflight could be: a system for building, repairing, and sustaining infrastructure in orbit, and a precursor to a more pluralistic landscape in which private vehicles increasingly share the stage with national programs. As spaceflight matured through the late 20th century, it became increasingly clear that the space age would not remain the domain of only two superpowers. Instead, a broader global landscape of space agencies emerged, each shaped by distinct national priorities, but connected by shared technologies, common scientific questions, and the growing significance of orbital infrastructure. This expansion did not happen overnight. It unfolded through incremental capabilities, such as satellite launches, scientific missions, and the development of indigenous launch vehicles, which collectively allowed more nations to participate in the economic, scientific, and strategic advantages of space. In this globalizing context, the history of spaceflight becomes not only a narrative of firsts, but a story of institutional diversification. Different countries built different competencies, sometimes emphasizing Earth observation, sometimes communications, sometimes navigation, and, more rarely and more expensively, crewed flight. Several milestones illustrate how this diversification began earlier than many assume. China launched its first recoverable satellite in 1975, and the same year, India orbited Aryabhata, signaling early national commitments to satellite technology and scientific participation in orbit. These achievements are historically significant because they represent the moment when space became a plausible arena for middle and emerging powers, not only as users of satellite services, but as builders of launch and spacecraft systems. Recoverable satellites, in particular, imply a higher level of operational sophistication. Recovery requires re-entry planning, tracking, retrieval, and often the management of payload integrity. For India, Aryabhata represented a foundational step toward building a national space identity and technical base. Even though early satellites may be modest compared with later systems, they function as institutional seed crystals. They create engineering communities, training pipelines, and political precedents for continued investment. Japan's early role through NASA, the National Space Development Agency of Japan, similarly reflects how national agencies pursued scientific satellites and launch vehicles as stepping stones toward deeper participation in space. The phrase "developed early scientific satellites and launch vehicles" captures an important strategy common across many spacefaring nations: build competence first in satellites and launchers, because these form the infrastructural base upon which more ambitious missions can later be mounted. Scientific satellites not only yield data, but also demand high reliability, power management, and precise instrumentation skills that translate into broader aerospace capacity. Launch vehicle development likewise creates industrial capabilities in propulsion, guidance, manufacturing, and systems integration, all of which are prerequisites for advanced missions. China's entry into human spaceflight in 2003, marked by Yang Liwei's mission, represents a later but strategically meaningful escalation from satellite capability to crewed operations. Crewed flight is qualitatively different from uncrewed missions because it requires life support systems, escape and abort considerations, stricter reliability standards, extensive training, and a mission architecture designed around human survivability rather than mere payload delivery. When a country develops crewed capability, it signals a willingness to invest in the most demanding end of the space capability spectrum, often for reasons that include national prestige, technological demonstration, and the long-term goal of independent access to orbital infrastructure. From the perspective of global space history, China's crewed milestone thus contributes to a multipolar environment. Human spaceflight is no longer concentrated in the United States and Russia alone. Meanwhile, Europe's role through the European Space Agency, ESA, illustrates a different model: multinational pooling of resources to achieve capabilities that would be difficult for smaller countries to fund independently. The fact that ESA astronauts became regular IS participants indicates how cooperation can substitute for fully national crew systems. Rather than building every element domestically, partners contribute modules, instruments, or mission support and receive crew flight opportunities in return. This arrangement highlights a broader truth about modern spaceflight. For many actors, the key goal is not national self-sufficiency in every subsystem, but reliable access to orbital research and operational platforms. Participation, in this sense, becomes a negotiated product of contributions, agreements, and shared governance. The IS era also revealed how interdependence can produce vulnerability. After the shuttle's retirement in 2011, Russia's Soyuz served as the sole IS crew transport from 2011 to 2020. This fact is historically important because it demonstrates that even the most advanced spacefaring nations can experience periods where access to orbit depends on international partners. The reliance on Soyuz reshaped operational planning, procurement, and scheduling. it also reinforced the strategic value of having multiple independent crewed transport systems, not necessarily because cooperation is undesirable, but because redundancy in access reduces single-point failures in international infrastructure. In a broader sense, this period illustrates how the space ecosystem behaves like other critical infrastructures. Resilience depends on redundancy, interoperability, and stable partnerships. In parallel with these developments, India advanced toward its own crewed program with Gaganyaan, reflecting another example of how national programs move from satellite expertise toward human spaceflight when political will, technical maturity, and long-term strategy align. The Global Human Spaceflight Club continues to expand, though slowly and at substantial cost. The importance of such a program is not confined to the eventual crewed mission itself. The path toward crewed capability tends to strengthen domestic aerospace supply chains, develop expertise in avionics and safety-critical systems, and deepen experience with launch operations. In other words, even partial progress toward crewed flight can have broader technological spillovers that increase a country's capacity in defense, telecommunications, Earth observation, and industrial engineering. As more national and multinational actors developed space capabilities, priorities also evolved beyond headline achievements toward shared problem sets that naturally invite cooperation. Expanded partnerships in sample return missions and shared scientific infrastructure, alongside a shift toward multinational priorities such as planetary defense and climate monitoring, illustrate how space activity increasingly intersects with global governance and global risk management. Climate monitoring, for example, depends heavily on Earth-observing satellites that provide consistent, long-term datasets across atmospheric, oceanic, and land variables. Because climate processes are global, no single country can observe the whole system from the ground alone. Space-based observation becomes a form of planetary instrumentation. Similarly, planetary defense tracking and potentially deflecting hazardous asteroids requires wide-area surveys, coordinated data sharing, and, in some scenarios, collaborative mission planning. The shift to these themes reflects a maturation of spaceflight's purpose. Space is not only a theater for national competition, but also a domain where shared vulnerabilities and shared scientific questions create incentives for cooperative frameworks. At the institutional level, this globalization has produced an increasingly layered architecture of participation. Some nations operate full-spectrum programs with launch vehicles, satellites, and occasionally crewed systems. Others specialize in instruments, modules, or scientific payloads. Still others participate as data users or as contributors to international projects. The result is a more complex and interconnected space community, where the flow of technology, expertise, and mission roles is multidirectional rather than centralized. Importantly, this complexity also changes the meaning of leadership in space. Leadership is no longer only about being first. It can also mean providing reliable launch services, producing indispensable instruments, maintaining long-term observation datasets, or contributing to international governance structures that keep large platforms like the ISS operational. In historical perspective, the expansion of global space agencies should therefore be seen as a structural transformation of the space age. It took spaceflight from a bipolar contest into a multipolar ecosystem, in which different actors pursue different goals, but increasingly share infrastructure and data. China's early satellite milestones and later crewed mission, India's early satellite achievements and move toward Gaganyaan, Japan's early launch vehicle and scientific satellite development, and ESA's sustained astronaut participation collectively demonstrate that space capability has diffused over time. The period when Soyuz served as the sole ISS crew transport underscores how interdependence can be both productive and constraining. motivating renewed attention to redundancy and partnership management. And the shift toward multinational priorities like planetary defense and climate monitoring illustrates how the motivations for spaceflight increasingly include shared scientific and civilizational goals that no single nation can address alone. While human spaceflight often dominates popular narratives, robotic exploration has been the steady engine that transformed the solar system from a collection of distant lights into a richly characterized set of worlds with distinct histories, environments, and scientific questions. The acceleration of robotic missions reflects a pragmatic reality. Robots can travel farther, remain longer, and tolerate harsher environments than humans, and they can do so at scales of risk and cost that enable a broader portfolio of exploration. A sequence of landmark missions illustrates how robotic exploration matured from early landers and flybys into long-lived, instrument-rich platforms capable of planetary orbiting, surface mobility, and even interstellar boundary crossings. This history is not merely a catalog of missions. It is a narrative of expanding methodological sophistication. Each mission class, landers, orbiters, rovers, flyby probes, answers different questions and forces different engineering trade-offs, and the cumulative result has been an extraordinary expansion of knowledge about planetary geology, atmospheres, magnetospheres, and the origin and evolution of the solar system. The Viking landers on Mars in 1976 represented one of the earliest moments when robotic exploration moved from reconnaissance to direct environmental interrogation on another planet's surface. Landing on Mars required solving problems analogous to lunar landing, but with additional complexity. An atmosphere thick enough to require aerodynamic considerations, yet thin enough to provide limited deceleration. Viking's success demonstrated that controlled descent to Mars was possible, establishing a technical template for later landers and rovers. Scientifically, Viking's importance lies in its role as an early platform for investigating Mars as a physical environment, measuring conditions directly rather than inferring them from remote observation. Even when particular experiments produce ambiguous results, their broader historical value lies in defining what is measurable and what must be measured better next time. In this sense, Viking helped set the agenda for later Mars exploration by clarifying uncertainties and motivating improved instrumentation and mission architectures. Only a year later, the launch of the two Voyager probes in 1977 initiated a different kind of exploration, one that leveraged gravity assists and long-duration power systems to conduct a grand tour of the outer solar system. Voyager's historical significance is amplified by its longevity. These spacecraft were designed to operate for years, yet they continued returning data for decades, eventually reaching interstellar space in 2012 and 2018. The phrase, "reached interstellar space," signals a remarkable extension of robotic reach beyond the heliosphere, demonstrating that spacecraft can become emissaries not only to planets but to the boundary conditions of the Sun's influence. Voyager's success also illustrates a deeper point about exploration infrastructure. A long-lived probe yields compounding returns. Each additional year of operation adds not only more data, but also new contexts in which to interpret older data, as comparative planetology evolves. A probe that outlives the scientific paradigms of its launch era can become even more valuable because it links generations of research, bridging different models and measurement frameworks. The 1990s and early 2000s broadened robotic exploration into more specialized and methodologically diverse missions. Galileo's arrival at Jupiter in 1995 marked a major step in orbital reconnaissance of a gas giant system, allowing extended study rather than a single flyby snapshot. Orbiting a massive planet with intense radiation belts and a complex moon system demands robust electronics, careful trajectory planning, and sustained data downlink strategies. Historically, Galileo contributed to the maturation of orbiter science. Long-term monitoring makes it possible to study dynamic processes, changing atmospheres, magnetospheric interactions, and time-variable phenomena that cannot be captured by brief encounters. Orbiters transform exploration from a visit into an observational campaign. Mars exploration, meanwhile, demonstrated a different trajectory, from static landers to mobile platforms. Mars Pathfinder's arrival in 1997 with the Sojourner rover created a new model for how surface science could be conducted, through mobility, imaging, and direct interaction with the environment across multiple sites, rather than a single landing location. The engineering and scientific logic of rovers is compelling. A rover can sample different rock types, traverse varied terrain, and place observations in geological context by relating features across distance. Mobility also introduces new mission constraints: power management, navigation, wheel-soil interaction, hazard avoidance, and the need for autonomous or semi-autonomous control. But the payoff is a richer form of planetary fieldwork. Rovers function as proxies for geologists, executing planned traverses and responding to discoveries in a way that static landers cannot. Cassini's launch in 1997 to explore Saturn further underscored how robotic exploration had become capable of large, long-term flagship missions aimed at comprehensive system-level understanding. Saturn, like Jupiter, is not a single target, but an integrated system of rings, moons, and magnetospheric processes. A mission designed to explore such a system necessarily becomes a multidisciplinary platform. Historically, Cassini reinforced the idea that planetary exploration is often planetary systems exploration, where the most scientifically compelling phenomena may involve interactions among a planet, its moons, its rings, and its electromagnetic environment. This systems perspective later influenced how scientists framed questions about habitability, because moons and subsurface environments emerged as plausible locations for complex chemistry and potentially life-supporting conditions. The 2000s marked a watershed in Mars exploration through the Spirit and Opportunity rovers, which transformed Mars geology by conducting long-lived surface investigations far beyond their originally planned lifetimes. The historical significance here is not simply that the rovers lasted longer than expected, but that their extended operations expanded the scale of the scientific program. Long-lived rovers can shift from initial reconnaissance to deeper hypothesis testing, following geological clues over time and refining interpretations as more terrain is covered. The transformation of Mars geology in this period reflects a broader maturation of Mars science. Mars ceased to be studied primarily as a distant analog of Earth, and instead became a world with its own distinct geological narrative, one that could be reconstructed through stratigraphy, mineralogy, and comparative landscape analysis. Curiosity's confirmation of ancient habitable environments in 2012 represents another step in this progression, shifting emphasis toward habitability as a central organizing concept for Mars exploration. The term habitable environments is carefully chosen. It does not claim that life existed, but that conditions in the ancient past may have supported it, an inherently testable scientific proposition that can be refined through chemical and mineralogical evidence. This focus matters historically because it restructures mission goals. Instead of asking only, "What is Mars like?" missions increasingly ask, "What was Mars like when it might have been capable of sustaining life, and where are the best records of that period preserved?" A rover designed with this agenda must carry instruments capable of detecting minerals formed in water, analyzing organic chemistry pathways, and interpreting sedimentary contexts. Perseverance's beginning of sample collection in 2021 continues this trajectory by linking rover science to future mission architectures, because collecting samples implies later retrieval, and return for detailed laboratory study beyond what rover instruments can do in situ. Sample return is historically important because it represents a methodological escalation. Earth laboratories can apply more sensitive, diverse, and repeatable analyses than can be packaged into a rover. By collecting samples, a rover becomes part of a distributed scientific system spanning 2 planets, Mars as the sampling site and Earth as the analytical center. This changes the temporal structure of exploration. Discoveries may unfold not only during a rover's active mission, but also years later when samples are studied with evolving techniques. Beyond Mars, robotic exploration continued to deepen understanding of the outer solar system. Juno's revelations about Jupiter's deep atmospheric structure reflect the ongoing value of specialized orbiters designed to probe internal dynamics rather than only surface appearance. A New Horizons' first close-up view of Pluto in 2015 demonstrates how flyby missions can still produce transformative leaps in understanding when they reach previously unvisited worlds. Pluto had long been a point of curiosity, but close-up imagery and measurements redefined it from an abstract dot into a complex object with features that could be compared and analyzed. Historically, New Horizons illustrates a recurring pattern in exploration. First encounters often overturn simplistic expectations, revealing complexity that forces new theoretical models. Taken together, this chain of robotic missions shows how space exploration matured into an iterative scientific process. Viking established the feasibility and value of direct planetary surface study. Voyager demonstrated the power of long-lived probes and gravity-assisted trajectories to explore multiple worlds and even reach interstellar space. Galileo and Cassini exemplified long-term system-level exploration through orbiting campaigns. Mars Pathfinder and Sojourner pioneered rover mobility, while Spirit and Opportunity expanded the scale and ambition of surface geology, and Curiosity and Perseverance reframed Mars exploration around habitability and sample return. Juno and New Horizons extended this logic to giant planet interiors and distant dwarf planets, showing that robotic exploration remains the essential method by which the solar system becomes a set of places rather than distant abstractions. As robotic exploration broadened across planets, moons, and small bodies, modern science missions increasingly pushed into domains where the primary challenge was not simply reaching a target, but executing complex, high-precision operations that demanded advanced autonomy, novel propulsion, and sophisticated instrumentation. Several emblematic achievements of this modern science mission era include Rosetta's first comet landing in 2014, asteroid sample returns by Hayabusa and OSIRIS-REx, India's Chandrayaan-3 reaching the lunar South Pole, China's Chang'e 5 returning lunar samples in 2020, the James Webb Space Telescope's launch in 2021, the Parker Solar Probe's exploration of the Sun's outer atmosphere, the expansion of Earth-observing satellite monitoring of climate change, the democratizing rise of CubeSats, and ion propulsion becoming a key. While these accomplishments are often narrated as individual triumphs, their deeper historical meaning lies in how they collectively demonstrate a shift in mission complexity and scientific ambition. Space missions are increasingly designed as intricate operations in their own right, with goals that require precise interaction with challenging environments rather than passive observation alone. Rosetta's first comet landing in 2014 illustrates this shift particularly well because a comet is not merely distant. It is a moving, low-gravity, irregular body with uncertain surface properties and an environment that can change dramatically as it approaches the Sun. Successfully landing on such an object requires navigation precision far beyond early planetary flybys, as well as mission planning that anticipates how weak gravity affects descent, anchoring, and surface interaction. The historical significance here is that a mission of this type transforms a comet from an object studied at a distance into a site of direct investigation, allowing the measurement of composition, structure, and potentially the organic chemistry pathways associated with early solar system material. Even more importantly, it shows that spacecraft operations can be designed to interface with small bodies in a controlled way. An operational capability that later becomes relevant not only for science, but also for planetary defense concepts and resource utilization discussions. Asteroid sample return missions extend this operational complexity by linking deep space rendezvous to the logistics of returning material safely to Earth. Both Japan's Hayabusa missions and NASA's OSIRIS-REx are examples of returned asteroid samples. Sample return is not just collect and come home. It requires carefully controlled touch and go, or landing operations under microgravity conditions, containment of material, secure re-entry packaging, and recovery procedures that preserve scientific integrity. Historically, these missions are significant because they strengthen the methodological bridge between planetary science and laboratory science. Remote sensing and in situ measurements are powerful, but they are limited by instrument constraints and mission time. Returning physical samples allow scientists to apply multiple analytical methods, revisit specimens as techniques improve, and test hypotheses in ways that spacecraft instruments cannot fully replicate. In that sense, sample return represents a maturing of planetary science into a discipline that can treat extraterrestrial material as laboratory evidence rather than solely as remote observation targets. Lunar exploration in the modern era also reflects both continuity and change. India's Chandrayaan-3, reaching the lunar South Pole, demonstrates a renewed focus on regions of the moon that were previously less accessible and that have gained strategic and scientific interest due to the possibility of volatiles and the unique lighting and thermal environment near permanently shadowed areas. At the same time, China's Chang'e 5, returning lunar samples in 2020, shows how lunar science is increasingly shaped by the logic of sample return and comparative chronology. Returned material enables refined dating, compositional analysis, and a more detailed reconstruction of lunar geological history. Historically, these milestones underscore that the moon remains a central laboratory for understanding early solar system history and for developing operational capabilities relevant to future sustained lunar presence. In parallel with exploration of nearby bodies, modern space science has pushed observational capability outward and backward in time through advanced space telescopes. The launch of the James Webb Space Telescope, JWST, in 2021 is a key example, an instrument designed to study the early universe. JWST represents a different class of mission challenge. Instead of navigating to a planetary target, the challenge lies in building an observatory with extreme sensitivity, stable thermal conditions, and precise pointing and calibration requirements. Space telescopes of this kind reflect the long-term evolution of space as an observational platform. Above Earth's atmosphere, instruments can access wavelengths and stability regimes that ground-based telescopes cannot. Historically, the significance of JWST is not only its scientific target, the early universe, but its demonstration of how space missions increasingly operate at the edge of instrument and deployment complexity, where success depends on the integration of large-scale optics, precise thermal management, and stable operational environments. The Parker Solar Probe's exploration of the Sun's outer atmosphere reflects yet another frontier, missions designed to operate in extreme thermal and radiation environments. Studying the Sun closely is scientifically vital because solar dynamics shape space weather, influence planetary atmospheres, and affect technological systems in orbit. But operationally, approaching the Sun requires heat shielding, trajectory design, and instrument survivability in conditions where solar intensity is far higher than in Earth orbit. Historically, such missions illustrate a key trend. Modern exploration increasingly targets environments that were previously inaccessible, not because they were too far, but because they were too harsh. Earth-observing satellites, monitoring climate change, further broaden the definition of space science by emphasizing continuity and measurement fidelity over dramatic one-time encounters. Climate monitoring is a multi-decadal scientific enterprise requiring stable datasets, calibration consistency, and global coverage. The historical significance here is that space systems become part of the planet's measurement infrastructure. Just as telescopes extend vision and microscopes extend perception, Earth-observing satellites extend the planet's capacity for self-measurement. This infrastructural role changes how space programs justify investment. The value is not only in exploration, but in providing data essential for understanding and managing Earth's environment, disasters, and long-term trends. The rise of CubeSats, democratizing access to space science, illustrates another structural change. Miniaturization and standardized spacecraft platforms allow universities, small companies, and smaller national programs to fly experiments that would once have been prohibitively expensive. Historically, CubeSats shift the mission ecosystem toward experimentation and proliferation. When small spacecraft can be built and launched more easily, the barrier to entry for innovation drops, enabling rapid iteration and niche scientific investigations. This does not replace flagship missions like JWST or major planetary orbiters, but it complements them by adding breadth. Many small missions probing many questions, sometimes in constellations, sometimes as technology demonstrators, and sometimes as focused scientific instruments. Finally, ion propulsion becoming a key technology for efficient deep space missions reflects how propulsion innovations continue to shape what exploration is possible. Ion propulsion is historically significant because it changes the trade space of mission design. Instead of high-thrust, short-duration burns typical of chemical rockets, ion propulsion can provide low-thrust over long periods, enabling trajectory flexibility and efficient velocity change for certain mission profiles. In a broader sense, this represents the continuing evolution of astronautics from the early rocket equation era to a more diverse propulsion toolkit. As mission goals become more complex, rendezvous with small bodies, prolonged orbital campaigns, multi-target tours, propulsion becomes less about raw power and more about efficiency, endurance, and precise navigation. Collectively, these modern science missions reveal how space exploration has matured into a discipline characterized by operational precision, methodological diversity, and an increasingly tight coupling between mission design and scientific questions. Rosetta and sample return missions show that spacecraft can interact with small bodies in complex ways. Chandrayaan-3 and Chang'e-5 demonstrate renewed lunar ambition oriented toward challenging regions and laboratory quality evidence. JWST extends the reach of observation toward the early universe, while Parker's solar probe extends exploration into extreme environments near the Sun. Earth-observing satellites and CubeSats highlight space as infrastructure and democratized experimentation, and ion propulsion points toward an expanding technological foundation for future deep space missions. In sum, the modern era is defined less by single iconic destinations and more by a broadened portfolio of sophisticated missions that together deepen knowledge of both Earth and the wider cosmos. In the early 21st century, the spaceflight landscape underwent another structural shift, one driven not primarily by new celestial destinations, but by changes in who builds spacecraft, how missions are funded, and what kinds of services are purchased, rather than directly operated by governments. This commercialization trend did not eliminate national space programs. Instead, it layered a new market-oriented ecosystem atop the existing governmental framework, with private firms increasingly providing launch, spacecraft development, and even crew transport as contracted services. Key milestones in this transformation include Dennis Tito becoming the first space tourist in 2001, NASA's Commercial Crew Program funding, private spacecraft development, SpaceX's Crew Dragon restoring U.S. crew launch capability in 2020, while Boeing's Starliner continued testing, the growing frequency of private astronaut flights, the expansion of commercial Earth imaging constellations, improvements in autonomous navigation supporting robotic missions, DART's first asteroid deflection test, and the forward-looking agenda framed by Artemis I. These elements, taken together, define a phase in which spaceflight increasingly resembles a mixed economy. Public agencies still set major exploration objectives and fund foundational research, while private actors provide hardware and services and pursue commercial markets. Dennis Tito's flight in 2001 is historically significant because it introduced the idea that access to space might be available not only to professional astronauts, but also to private individuals under certain conditions. While space tourism can be dismissed as a novelty, its deeper importance lies in how it signals the possibility of non-government demand for human spaceflight services. Even a small market can influence institutional thinking. If private individuals can purchase flights, then spacecraft and stations may gradually be designed with different operational assumptions. Customer experience, repeatability, and service reliability become part of the discussion. Tito's milestone thus serves as an early marker of a trend in which human spaceflight may broaden in participation, even if professional crews and scientific missions remain central. NASA's Commercial Crew Program represents a more systematic and transformative approach to commercialization because it explicitly used public funding to stimulate private spacecraft development rather than relying exclusively on government-designed vehicles. This programmatic choice is historically important. It reflects a procurement and innovation strategy in which the government acts as an anchor customer, shaping requirements and providing funding while allowing companies to develop designs within broader commercial ambitions. In this model, the government's goal is not only to obtain a service crew transport, but also to nurture an industrial base capable of competition, innovation, and potentially lower costs through economies of scale and multiple customers. The emphasis on program is key. Commercialization here is not ad hoc, but an institutionalized policy approach that aims to reshape how space access is provided. The restoration of U.S. crew launch capability in 2020 via SpaceX's Crew Dragon illustrates the tangible operational outcome of this approach. Historically, this milestone also closes a chapter opened by the shuttle's retirement, after which the United States lacked domestic crew transport capability to the ISS for a period. The return of U.S. crew launch capability changes the resilience of ISS operations by increasing redundancy and reducing dependence on single provider access. More broadly, it demonstrates that a private company can develop, certify, and operate a crew-capable spacecraft in partnership with a national agency, a model that may influence future exploration architectures. Meanwhile, Boeing's Starliner continuing testing underscores a second structural feature of commercialization, competition, and parallel development. Having multiple systems can improve resilience and provide alternatives when one system experiences delays or technical issues, though it also introduces complexity in oversight and integration. The growth of private astronaut flights further reflects the diversification of human spaceflight roles. When flights are conducted outside the traditional National Astronaut Corps on governmental missions, paradigm, mission purposes broaden. Some flights may focus on research, others on training or demonstration, and others on private objectives. Regardless of the particular mission purpose, the historical significance is that human spaceflight begins to develop multiple use cases, which can influence vehicle design, station utilization, and the long-term economics of orbital infrastructure. Private flights also interact with another major commercial trend, the expansion of commercial Earth imaging constellations that provide global mapping capabilities. Constellations alter the logic of observation by prioritizing temporal frequency and coverage. Instead of a few exquisite satellites, constellations use many satellites to revisit locations often, enabling near-continuous monitoring that supports applications ranging from environmental observation to logistics, agriculture, and infrastructure assessment. This proliferation depends on launch availability and costs, connecting commercial satellite growth to the broader evolution of launch services and reusability. Autonomous navigation improvements, supporting robotic missions, are another key enabler in this era. As missions become more complex, rendezvous with small bodies, precise landings, coordinated formation flying autonomy becomes less optional and more central. Communication delays and limited bandwidth often mean spacecraft must make some decisions locally, at least within constrained parameters. Autonomy also supports the management of large constellations, where human operators cannot micromanage every satellite. Thus, improvements in autonomy are historically significant, not just as incremental software advancement, but as a structural enabler of scaled space operations, both scientific and commercial. One of the most consequential demonstrations of modern capability is DART, described as the first asteroid deflection test. DART's significance is that it moves planetary defense from conceptual discussion into operational experiment. In historical terms, this represents an evolution in how humanity relates to the solar system, not only as a set of objects to study, but as a dynamic environment where hazards exist and mitigation is conceivable. A deflection test necessarily involves precision targeting, trajectory prediction, and measurement of outcome, linking deep space navigation and small body science to a civilizational risk management objective. Even a single test does not solve planetary defense, but it establishes a proof of feasibility that future strategies can build upon. The forward-looking exploration agenda is framed by Artemis 1, testing NASA's Orion spacecraft in 2022, and by plans for Mars sample return and lunar resource utilization, shaping the next phase of exploration. Artemis 1's test is historically important because it signals renewed emphasis on deep space crewed systems after decades in which low Earth orbit infrastructure dominated. Testing Orion is not simply a hardware milestone. It reflects an architectural commitment to missions beyond low Earth orbit, with the Moon as a staging ground for further exploration. The mention of lunar resource utilization indicates that future exploration is increasingly conceived not as a series of self-contained sorties, but as a process of building sustainable capabilities. Resource utilization implies extracting or using local materials, such as water ice for life support or propellant, so that missions can rely less on supplies launched from Earth. While the specifics of implementation vary, the strategic concept is historically significant. It marks an intent to treat the Moon not only as a destination, but as a site where infrastructure and supply chains could eventually be developed. Mars sample return planning similarly indicates a future in which exploration becomes distributed across multiple mission elements, requiring coordination among orbiters, landers, ascent systems, and Earth return vehicles. Sample return is, by nature, a multi-step architecture that integrates planetary protection considerations, precision landing and retrieval, and secure Earth re-entry. Its appearance alongside Artemis suggests a future in which human and robotic exploration are not separate tracks, but interlocking strategies. Robotic missions gather samples and data, while human-oriented programs build transportation and staging capabilities that could eventually support more sustained presence and broader scientific work. In sum, the commercialization era is best understood as a transformation in the structure of spaceflight, rather than simply a set of new missions. Dennis Tito's flight introduced private participation. The Commercial Crew Program institutionalized public-private development. Crew Dragon restored U.S. crew launch capability, while Starliner continued testing. Private astronaut flights broadened mission roles. Commercial constellations expanded Earth observation into a high-frequency, service-based model. Autonomy improved the scalability of operations. DART demonstrated these developments collectively suggest that the future of spaceflight will be shaped by the interaction of public goals and private capabilities, where exploration, infrastructure, and commercial services evolve together rather than in isolation. Today, space is no longer just a distant frontier. It is part of how our civilization functions, how we understand our planet, and how we imagine our future. Satellites quietly guide navigation and monitor a changing climate. Robots explore worlds we may never visit in person. Humans live and work in orbit, preparing for journeys that will carry us farther than ever before. Yet every launch, every discovery, and every mission traces its lineage back to the same fundamental shift in thinking: the realization that the universe is governed by laws we can understand, and that distance is a challenge to be solved, not a boundary meant to confine us. Spaceflight did not emerge from a single moment of inspiration, but from centuries of curiosity, persistence, and the willingness to turn ideas into action. And as new generations look outward to the moon, to Mars, and beyond, the story of spaceflight remains unfinished. It is still being written, not only by rockets and machines, but by the enduring human belief that exploration is both possible and worth the risk. I hope you enjoyed this review of the history of space exploration. For more videos like this, like and subscribe. Ring the bell. Until next time.